This is Unit 8, Video 1. In this unit, we will talk about solutions, a very important concept in chemistry. Let's begin by defining a solution. A solution is defined as a homogeneous mixture, which, remember, means it is perfectly mixed of two or more substances. Now, we separate a solution into two parts. The first part is called the solute, which is what's being dissolved, and the second part is the solvent, what is doing the dissolving. So in the example here, we're pouring some sugar into water. Sugar then would be the solute, because it will be dissolved by water, which is the solvent. And the solute should be uniformly dispersed. This uniformly just refers to the fact that it has to be homogeneous for it to be considered a solution. And it has to be completely dispersed. In other words, you can't have clumps of the solute hanging around. That actually would not be a solution. And the way we define solute and solvent is the one you have more of is the solvent, the one you have less of is the solute. A way to remember that is by counting the number of letters. In solute you have 1, 2, 3, 4, 5, 6 letters. In solvent 1, 2, 3, 4, 5, 6, 7. You have 7 letters, so that is what you have more of, the solvent. Now, solutions don't have to be a solid and a liquid. It doesn't have to be salt and water or sugar and water. You can have any state of matter being dissolved in any other state of matter. A famous example of this is brass. This is the alloy brass, and these are alloys. And these are essentially two metals mixed together, a solution made from two metals. So oftentimes what they do is you can melt the two metals in their liquid state and then allow them to solidify, and you get a perfect solution. And same thing with many rings are actually not pure. Even if it says a silver ring or a palladium ring or a gold ring, it usually is a mixture of a few other metals to make it stronger, more durable, and so forth. So this is a solid and a solid. The example here is a gas dissolved in a liquid. So soda has little tiny bubbles of carbon dioxide, quite a bit of it. If you allow all the carbon dioxide to escape at once, you may have seen the big fountain demonstrations with throwing something inside like a salt or Mentos is usually used. But in this case you have a gas dissolved in a liquid. So you can have any state in any other state. Two gases mixed together is the solution we call air. So air around us is technically a solution. And you can even have a solid dissolved in a gas. And an example here is hydrogen and palladium. Strange but true. So any phase of matter can be dissolved in any other phase of matter, if the particles are uniformly dispersed, that is. Alright, now solutions can be electrolytes, which means when they dissolve, they'll conduct electricity. And this happens because they separate into ions. They actually form ions. So we can form ions. In the classic example of salt dissolving in water, salt, sodium chloride, separates into sodium, represented here by the blue, and chlorine, or chloride, represented by the green, and they separate so you can actually conduct electricity in the solution. And this usually refers to ionic compounds. Ionic compounds will form electrolytes. Non-electrolytes, an example of it would be sugar, dissolve but don't conduct. They dissolve in water, so sugar is very soluble in water, but they do not conduct electricity because they do not form ions. So covalent compounds usually fall into this category. And then if you recall, we also talked about something in the middle, weak electrolytes, which partially conduct. So you could have a substance dissolved in water that some of the molecules break apart, but most of them do not. And this happens in the case of weak acids or weak bases, if you recall. So solutions could be electrolytic or non-electrolytic. Now, we're going to talk a little bit about how this dissolving process works. Remember, you have intermolecular forces holding the molecules together. So between solute particles and between the solvent particles. So in a solution, here it says the intermolecular forces between solute and solvent particles must be strong enough to overcome those between solute particles and those between solvent particles. So in other words, when you form a solution, which is between solvent and solute, that strength must overcome the strength of the solvent between each other and the solute between each other. So the example here is there is a force of attraction in this salt. Technically, there's a very strong force of attraction here. And you have to overcome this force of attraction. So the new attractions that are made, here you have water molecules actually carrying away these ions. This new attraction that forms has to be stronger than the original attraction. And that's usually what happens when it dissolves. And here it says, as the solution forms, the solvent pulls the solute particles apart. That's what you're seeing happen here. Water molecules are pulling apart. We'll say this is sodium chloride. We can say back this is salt. And this is called solvation, process of solvation. Now, the preacher talks about salvation on Sunday. This is a little different. This is solvation, also an important process. So this happens with ionic or with covalent, with any type of substance. But that's the picture that you would see. If you can watch them happen, this will be exactly what happens. And when they get solvated, what happens is each ion, in this case sodium, will be surrounded by 6 water molecules. And you'll notice that the oxygen, which is the negative part of the water molecule, is oriented toward the sodium ion. And in the case of chlorine, the hydrogen, which is the positive part of the water molecule, is oriented toward the chloride. So in this case, usually it's 6 around. Usually you get an octahedral type of arrangement around these. So these new bonds are called ion-dipole interactions, because you have an ion, which is the chlorine, and this is a polar molecule, so you have a dipole set up here. A dipole is a positive and negative side on a molecule. So these are ion-dipole interactions. Between water, what you had dipole-dipole, or hydrogen bonding interactions, and now you're going and using those to bond with the chlorine and with the sodium. And here it says, in order for this to happen, the lattice energy of the salt must be overcome. Remember, the sodium chloride bond, that had a lattice energy which had to be overcome in order for it to break apart, which is the lattice energy is a pretty strong bond, and water is able to overcome it. And this explains why some substances are soluble, others are not. So sodium chloride, for example, is soluble because the ions being +1 and -1 aren't as strongly attracted as calcium oxide, which is +2 and -2. There's a stronger attraction here, and if you remember from the solubility rules, calcium oxide does not dissolve in water. The lattice energy is too strong for the water to overcome, and that's kind of the idea here. So it is, in other words, this is an idea of breaking bonds and making new bonds. It's not a chemical change, it's considered a physical change, but there is energy involved, and that's what we're going to look at next. So the energy change involved in the solution process, in the case of sodium hydroxide, if you throw it into water, make it aqueous, it splits apart. It's technically an ionic compound, so it's an electrolyte. Notice how big the delta H is, -44.5 kilojoules per mole. That is quite significant. You'll definitely feel a lot of heat when you dissolve sodium hydroxide in water. I've done it many times, and the water gets pretty hot as you do this, especially if it's very concentrated. So the way this works is we're going to keep track of the breaking and the making of bonds. So first you have to separate the solute particles apart. This would be, in this case, the sodium hydroxide. You also have to separate the solvent particles apart. That would be water. And then you have to make new interactions between water and those solute particles. And that's how we have this represented as aqueous. This means we're dissolved in water. So we're going to take a look at these energy changes. So the first 2 steps, you have separation of solute molecules or particles. This is endothermic. So anytime you separate particles, anytime you break bonds, it is endothermic. It requires energy. Delta H, remember, is positive. This means greater than 0 means positive. So here we're breaking the attractions between the solute. Same thing happens when you break the attractions between the solvent. That's also an endothermic process, also requires energy, and it is positive. So this is always the case. The first 2 steps are going to be positive. They will be endothermic, require energy. And then the last step, when you're forming the new bonds, so in this case, you've got the solute particles, which have been broken apart, the solvent particles broken apart, you're about to put them together. This is an exothermic process because you're forming bonds. If breaking bonds required energy, then forming bonds releases energy. In this case, delta H is less than 0, which means it's negative. So the whole process, the heat of solution, we can call this enthalpy of solution. Remember, enthalpy is the fancy word we use for heat, enthalpy of solution. For this process, you'd have to add up all these processes. So because these were positive, and this was a positive, this turned out to be a negative. So if the negative is greater, and usually it is the case that the negative is greater than the two positives, then your overall heat of solution becomes negative, and the molecules release energy. And here it says it depends on the strengths of the intermolecular forces. So if these intermolecular forces were very, very strong, you have to put a lot of energy into it. If these were very strong, then this negative would not be able to overcome it, and your heat of solution would be positive. It's possible for the heat of solution to be positive. And there is another fun concept that we won't get into in honors chem called entropy that explains why endothermic reactions, which are difficult to understand, well, why do they form if it takes so much energy? Doesn't that go against nature? Well, something called entropy related to disorder actually explains it. So here we go. The examples of this are, I got two examples up here. The first is good old sulfuric acid. I picked sulfuric acid because it has one of the highest heats of solution of any substance. Notice almost 100 kilojoules per mole. That is incredible. That's quite a bit of heat. You'll definitely get scalded. In fact, there's a safety rule in science or in chemistry where you're supposed to add acid to water and not the other way around. Because if you add the water to the acid, the solution heats up so fast, so much that it can actually boil and splatter in your face and injure you because of sulfuric acid. So this is actually a safety rules based on this high heat of solution. Quite a bit of heat gets evolved. On the other side, I picked another substance, ammonium nitrate. It has a very high positive heat of solution, a very endothermic. Now this is not as high as the sulfuric, but this is actually pretty high for endothermic reactions, as endothermic reactions run. And the reason for this is because there's actually hydrogen bonding that keeps these together. These two ions are kept together by hydrogen bonding, since you have yourself and an H. And that requires a lot of energy to break those solute particles apart. Because it requires so much energy, then the overall process actually ends up being positive. Which is neat. You can actually, when you make this solution, if you put your hand on it, it's really neat. It actually cold. It's cold. It feels very cold. Heat is actually being absorbed into the solution. And an interesting fact is whenever you're dissolving gases, the process is always exothermic. Now, scientists had noticed this, and the question was, this is interesting. Anytime you dissolve gases, it's exothermic. Why is that? Well, because the positive of breaking apart the solute particles does not exist. Remember, gases, like in the case of NH3 here, don't have any attractive forces between them. So that positive that you have to put energy in to break them apart is gone. So you have essentially a lot of negative. Well, you still have to break apart the solvent particles, the water, but the new solution that forms usually overcomes that quite easily. And here is ammonia. This is also hydrogen bonding, possible with water, has a pretty high heat of solution, -30. That's considered pretty high for just a physical change. Good. All right, we're going to try to, I think we'll kind of wrap up there, and we'll talk about making solids in the next video.